Hey everybody, it is October 26, 2018. Here's the topic, and I may even do one more about igneous rock classification, but we'll get to that a little bit here, but not in any great depth. Back in July, we visited Devil's Tower, and I have not been there since field camp, and I don't remember. We just walked around it for a couple of hours, didn't really look at it in detail or anything, and I don't remember much about it. I do remember the columnar jointing, which I'm going to talk about here in this intro, and then I am going to show you, as we were walking around in July, I believe it was July 23rd, I'll correct it if it's not, we walked around the tower and I was looking at it more closely than I ever had done before, and I was formulating some ideas in my head to see what this is, because Devil's Tower is somewhat of a geologic enigma. This is Blackie. We actually do not know how this thing formed. We have several hypotheses, and there's a leading one now that came out in 2015. All the references to this will be at the very end, past the credits. So if you want to look at those, you'll see them. But even though we don't really know how it formed, there's several competing ideas. This 2015 idea, at least was testable. They modeled it, and they came up with something that would resemble a structure like Devil's Tower. So it's probably the best working hypothesis we have. But before I get into that, and before I show you the video of us walking around the tower, what you're seeing here is just a simple cross section through the earth, through scale, not to scale or anything. The light blue is the sky, the brownish color is the earth, and the light blue is water. And the reason why I'm showing you that is because I'm going to show you how columnar jointing forms. Okay, what happens is you get a magma body that comes up through the earth, starts intruding into the country rock. It may start to split and form a sill as it continues to rise, and it's still not solidified, it's still magma. And it gets to the surface and erupts as lava. Some of it remains as magma. You get this little ball here, which is kind of like a magma chamber. For some reason, it can't go any further to the right in the country rock. It just kind of pulls there. Well, we'll say this cools relatively quickly, okay? So what happens? All right, so as it starts to cool, these lines you see here, this is columnar jointing. Now, bless you, Blackie. Okay, so this columnar jointing starts to form. And if you notice something, it forms perpendicular to lava flow. So in this example, the lava has come up from underneath and spread out. And the columnar jointing will form perpendicular, really close to that, which is 90 degrees from the direction of flow. So as this stuff cools, you start to get that, but where it hit the water, it did something weird. Well, what is that? That is what we call tablature jointing. Okay, the more traditional columnar jointing is the colonnade form, the straight lines, which is what we're going to deal with because the Devil's Tower does not have this entablular stuff. But anyways, you get that more chaotic columnar jointing when it intrudes a surface body or when the lava, while it's still molten, hits a body of water and starts to cool. But when you don't have water involved, you get the typical column-looking columnar jointing. And that's what happens. So eventually the thing's going to totally cool, and you're going to get this pattern. What do we see? It's kind of weird. So Devil's Tower, this is roughly the sediments that it has intruded, that the magma intruded. I'm going to talk about those later too, but the basic shape of it, and you get this kind of rise up, which most of it's tailless. And then you get the tower itself, which kind of looks like that. It does kind of lean this way to one side. What you see in the joints as you go up, you see this columnar jointing, but it doesn't go all the way through. Like this just has typical joint and fracture patterns on the one side. You'll see it in the video. We're going to walk around it. But most of the columnar jointing, where it is present, does something like this, where it'll be straight here. It's extremely weathered, like in the upper quarter. So indicating that this part here was exposed to the surface for a long time, slowly weathering. And it's more fresh here. And what you see as this goes up is you see the jointing will change direction. And that's where the confusion comes in. Well, actually, the best working theory is that this was some sort of diatreme. And I actually thought this was an arm, because if this is perpendicular to lava flow, what if this was at one time an extensive surface flow with columnar jointing, and this was your ground level at the time, and this here would be the magma chamber kind of stopped before it started erupting, or while it was erupting, giving you the change in joint patterns. And if it's a diatreme, that's kind of what happened. This older theories say this is a volcanic plug, or this was a magma chamber, but when they did the 2015 paper, the diatreme idea kind of showed how you cannot get columnar jointing from a volcanic neck or from an underground magma chamber that doesn't erupt on the surface with this pattern. Okay, so we can kind of rule those out, but not definitely. Okay, so where are we spatially? Where are we located on Earth, and specifically in the United States and within Wyoming? Where is Devil's Tower? Well, first I'm going to show you the location of the closely related Missouri Buttes. You can see the arrows here. There's the west and east, but there's more than just those two. Those are just the two most prominent. Here's Devil's Tower National Monument. You see all this red looking stuff here? That's all sedimentary rock, okay? And it's not very well consolidated. The red stuff is the Spearfish Formation, and I actually remembered that from field camp because that formation tortured me. It's Triassic in age, lower Mesozoic. Here's some statistics on it if you want to read it. Just some background information, what else it's known as, the first people that climbed it. And here is some other statistics, like from the base to the top. It's 867 feet. Some people have it at 12 and some odd change, but this is from the top of where the talus is. I erased it. Top of where the talus is to the top, not from like the beginning of the trail to the top, because that's significantly lower. And the main type of rock, and we're going to talk more about this in detail after I show you the videos, but it's a phonolite trachyte porphyry, which is kind of coarse-grained, and it's related to syenite. And is it plutonic? Is it volcanic? This is one of those rocks that's in a gray area. Not everything is so easy to classify, and this is one of those situations. Now, as we zoom out a little more, you can see the relationship between the Buttes and Devil's Tower, 5.35 kilometers, or roughly 3 1/3 miles. Real close to that. That's how far apart they are. So although they may not be the same intrusion, they are related, probably from the same magma chamber. Here's a Geologic Map Overlay of the area, and you can see the reds represent the igneous flows and everything else, so sedimentary rock had intruded. Here is a stratigraphic column of all the rock units in the area and their interpretation of a cross-section on top. I have my issues with that. But as we zoom out some more, you can start to see US 14, and here's that same Geologic Map Overlay. You can see we're slowly zooming out. And Devil's Tower Town shows up for some reason. Now this red or orange and yellow marker shows you we're too small to show you the map, but what you see here is the Black Hills, and this is a Geologic Map Overlay because the tower is related to the Black Hills. That's why I'm showing you that. And it's in northeast Wyoming. The Black Hills cross the border from western South Dakota into northeastern Wyoming. So that's where we are on the map. Okay, and you can see the surrounding states if you want. Once you start driving towards Devil's Tower, you start to see how strikingly different this feature is to the surrounding landscape. Sorry, I couldn't help myself there. So as we continue on, you see the red Spearfish Formation, the Triassic one, a lot of sedimentary rocks, sandstone shales, things like that. And you can see just the tower, it's just so out of place. It's no wonder people love this thing and have wondered about it. And the Native Americans thought a bear carved it out with his claws.
Okay, so there is Devil's Tower. Now, there, from a geologic standpoint, we actually don't know how this thing formed. You go inside, there's a thing saying it could have been a volcanic plug or a stock or a laccolith. There's problems with all those. Number one, their origin's similar and they're all underground. The problem with it is you see these long lines here. That's called columnar jointing. I don't know if anyone's ever drilled in the middle to see if it gets coarser towards the middle. And I also don't know if it's hexagonal on top. I have no idea. If I find out, I'll let you know. But the problem with columnar jointing is, see how they go that way? Well, columnar jointing forms perpendicular to lava flow, which means it would have to be this way. So that can't be a volcanic plug. That can't be a laccolith. It can't be a stock. At least not on ground. It could have been a huge massive sill and everything else is eroded, because if you look down, it changes direction. This could have been an intrusion that came up and had different dimensions to it, and this is the only thing that remains. I mean, we really just don't know. Like I said, it could have even been a surface flow that was much more extensive. Like I said, it's kind of a big enigma. Well, this boulder fell from up there. This stuff's pretty coarse grained.
The rock type, I'm just going to touch on it real quick. It's either phonolite or trachyte. Dominantly, these are rare rocks.
In the talus here at the bottom, you see a lot of fracturing and jointing. It's almost at 90-degree angles, but this is fallen from up there. Now, what you can see from here, see the columnar jointing and how it changes direction and then disappears. It's not in the whole thing. This rock here is typical jointing and fracturing, which generates a lot of this talus. So there is no columnar jointing there, and as it comes down, it just kind of tapers out just on this one side and spreads out. Well, that's about the only part we know of. So like I said, the problem with all these, we see sandstone and shale. The red stuff seems to be shale. Lighter stuff seems to be sandstone. But the problem with all those is they all form in a similar environment. Like I said, it still doesn't explain the vertical columnar jointing. Okay, that red is the spearfish. That tan right there is the sandstone. And if you look and come over here, it's a lot lower than the tower is. So even if there was more sediment here, stacked up higher, I don't know. It could just be that could have been the surface, and then this could have been the surface flow. Here it is better. That could have been the old surface. Intrusive, extrusive. I would love to see if the actual columnar jointing is finer grained. So it looks like most of the talus is weathering from near the bottom here. But you can see some blocks higher up. Obviously, some of the columnar jointing has fallen. As you can see from this side, visitor center, I think is that way. The columnar jointing just kind of disappeared there. That was the first side. We're coming around. See, the columnar jointing comes down this side further. Disappears again over there. There's the entrance. And then you can see here as we pull back further, see how the columnar jointing turns real hard, and then we're getting near that side where it disappears again for a little bit. But it's straight here, it just kind of comes down and breaks that way here, and then kind of disappears again over here. The only part that's consistently columnar jointed is the top part. So apparently there are people up there. I'm gonna have to, Dave said 2. I'm not gonna look through the binoculars. Sarah's camera has killer zoom, so I'll just go through it later. and show it. But apparently they're where, Dave? Right near the bottom of the green? Of the vegetation or something?
Yeah, you can actually see them without. Do you see the vegetation?
Yeah.
Totally on the right.
This part right here, that is the top, columnar jointing, the fracturing, which I suspect is fracturing, probably is. That right there is probably due to frost wedging. And in the winter, water will seep in through the cracks, freeze, push them open a little wider, melt, following year, come next winter, process repeats itself until eventually something's pushed downhill, which is probably what a lot of this is. Now, as we're getting higher, columnar jointing again, fracture patterns, and then there's this thing, big piece that fell at some point, all cracked up. Symmetrical columns, this is columnar jointing. That's what they're showing, but that is not columnar jointing. That is, and this is probably a victim of frost wedging. That looks like, if I wanted to measure this, I could probably see if it fell out of there or something like that. But yeah, that's a pretty good exposure of the rock. No idea what that screeching is. No, there are no monkeys here. Coming out of the shadow. Apparently, halfway point of the trail. So that sign Sarah went to go look at,
There's a weird.
says a trail's closed because of super aggressive falcons, and I'm not wondering if that's...
Climbers are advised to be aware of territorial aggression from nesting falcons. If falcons exhibit a defensive, distressed behavior, descend off the tower at the next safe opportunity and report the incident to a ranger.
I wonder if that's what that noise is. Now on this side, past the halfway point, columnar jointing does come down a lot more. Over here. There's the buzzards, real clear. Good thing we stopped here to have sandwiches for dinner. But there's the Devil's Tower. There's a weird art thing Sarah's going to. I guess now I can see the relationship between the spearfish, the gypsum layer, the shale, and the sandstone, and the igneous body that is Devil's Tower. This is that the sandstone comes right up to right about there. So the tower is above the sandstone. At least what hasn't been eroded.
No, it stopped. It hurt for a while.
Okay, so now that you saw the video of us going to Devil's Tower and driving around and exploring it, trying to figure this thing out, and me pointing at things, we need, before we can start talking about the origins of Devil's Tower, we need to talk about the rocks themselves, the rocks that comprise this thing, and the rocks of the surrounding area. Well, what you see here is you see a very generalized stratigraphic column of the rocks near Devil's Tower and of the Black Hills. Now, key thing to remember about the Black Hills, it's a very complex area geologically, and here's the geologic map, the best one I could find with some cross sections showing you that again. But the thing here is there's a lot of Precambrian rocks involved that have been really altered and deformed along with the above-lying rocks. So we're not going to talk about those because they don't outcrop at Devil's Tower or Missouri Buttes. What you're seeing here is pretty much the sedimentary rock record. And the rocks are pretty flat lying for the most part. They do slightly dip. This slide here is taken from a petrology class. It's the people that actually did the chemical analysis of the rock that makes up Devil's Tower. It's very homogeneous. As well, for igneous intrusion, for igneous rock, it's very homogeneous. The crystals are a little bigger, and this is what we're going to talk about what we mean by plutonic versus volcanic. And where do we draw the line? Well, there's actually a standard for this, but the standard itself is kind of iffy, but I'll save that for classification of igneous rocks. But as you can see here, there are some good sized crystals in here, a lot bigger than 3 millimeters. And from the drawing I showed you before of Devil's Tower and from what you've seen in the video, we have a strong suspicion that the top part is volcanic and the bottom part is plutonic. So even though the thing cooled pretty much consistently, you've got plutonic and volcanic rocks that make up the tower. So that kind of complicates classification too, and I'm getting that here in a second. Now what you're seeing here is what we call a TAS diagram. You only use this if you have actually done chemical analysis in one way or another. And what these individuals did was they ran some tests and they came up with most of the rock as a trachyte. Now their sample size wasn't huge. Others have described it as a phonolite. Others have even described it as a syenite. And it does vary lithologically from area to area. There is some quartz in this rock in places, and others places there isn't any. So it confuses things. Well, here's a chart, a QAPF diagram for plutonic rocks, okay? And plutonic coarse grain rocks, rocks that form underground. But you know, here's the thing, that blue circle, dashed line circle, is about where everything plots. As you can see, it's over an area. Quartz cannot form if void minerals form. The two can't, it's not a physical possibility, okay? If you get voids, you will not have quartz. If you have quartz, you will not have voids. And quite honestly, rocks containing voids like phonolites and trachytes are below the void, below the A and the P that you see there. Those are very rare. And Devil's Tower is one of those. Now, there are some parts that do seem to have a little bit of quartz in them, so it would actually plot a little bit above. So it's really just potato. And here's a volcanic rock QAPF diagram. And as you can see, most things plot in the trachyte, void-bearing trachyte, and maybe a little bit in the phonolite. Like I said, this stuff does have quartz in it. That's why back earlier in the location video, it said, you know, I had phonolite / trachyte, also syenite, because it's really matters. I mean, if you just saw a rock from Devil's Tower in a box, you could pretty easily tell it's igneous. It's porphyritic right away, meaning it has large crystals in it, which we've seen from the other slides. And you would probably think it was a plutonic rock. Some of it is, some of it isn't. But, you know, see, so everything in geology isn't black and white. So how big are these columns exactly? They're pretty big. Sarah's camera has killer zoom. Here, as you can see, the top kind of gets rounded weathering. It's a lot more weathered than the stuff on the bottom. It's more rounded. There's fractures all over the place, perpendicular columnar jointing. But just how big are these? Watch this part as we zoom in a little bit, right where it goes from smooth to weathered rock. And here are two people on it. So these joints are, columnar jointing is huge, on the orders of 10 to 20 feet in diameter and hundreds of feet long. I wish I had a piece of Devil's Tower to show you, but I do not, alas. But now that we have talked about the porphyritic rock that makes up the tower, we can start to talk about its origins. What you're seeing here is a generalized generic cross-section I made. There's no scale on here, as you know. The red stuff on the left are the Missouri Buttes. The red thing on the far right is Devil's Tower, with the surrounding formations from the outdated nomenclature I use basically just to show you that the rocks are pretty flat-lying or level. We can see the Paleozoic formations, the Mesozoic, and Devil's Tower and the Buttes, Missouri Buttes, are Cenozoic. All right, that's what that's showing you. Here's where they both are. Like I said before, they're about 3 1/3 miles apart from one another. Here's the radiometric ages. The buttes are 49.24 plus or minus 0.28 million years ago. Devil's Tower is 49.04 plus or minus 0.16 million years ago. And that's argon-argon dating. Now, the thing you can see here is the margins of error kind of like overlap. So we take the 2018 geologic time scale that GSA released, and we put this frame onto the geologic time scale, and we see it's Eocene. The green lines are the exact dates. The reddish line that encompasses the green lines all the way across on the margin of error. So as you can see, this is possibly the same intrusion. It is not likely that it is, but it is very likely that it's the same magma involved. Missouri Butte rocks do differ slightly. The rocks contain more country rock inside of them. That means they picked up a lot more of the rock they moved through, because that's your surface. As rocks come up, as magma rises, it's going to absorb the surrounding rock and incorporate it into the magma, okay? And if it fully incorporates it, you'll never know. But Missouri Buttes, it doesn't seem to have done that in places. There you see a lot of the country rock actually in the igneous rocks itself, inside the lava. So it likely is not the same flow, but did form from the same magma chamber. And it's a lot easier to explain than Devil's Tower. The old traditional view, well, how did we used to do this? And we even did this at field camp, I remember this. Whenever we had intrusion mapped at the surface, like the Missouri Buttes or Devil's Tower here, we would just draw these volcanic feeder tubes, which we called soup cans. Now, that doesn't make any sense because it's not going to give you the columnar jointing pattern of Devil's Tower. So what does the columnar jointing tell us? Here I've added just a rough draft, or rough outline of what the columnar jointing along the tower is. Well, let's try to backwork this. What would have been the situation about 49 million years ago when this stuff was deposited? As you can see here, I added some white layers, which would be eroded now, they're gone. Some purple, which would be, the purple and red are actually the same lava flows. It's just the red remains today, the purple's been eroded. I just wanted to make that distinction here. And you can see the columnar jointing, and you can see that if Devil's Tower was a surface flow, how at the top you would get the vertical columnar jointing, and further down you would get the splayed out, the kind of coming down columnar jointing we see near the base. So, this is kind of like an inverted laccolith, and Devil's Tower has been described as being a laccolith before in the past. It's just usually laccoliths are domes. It's just usually as laccoliths come up through the earth, they tend to form a dome shape. That's a very generic example, but Devil's Tower seems to be something inverted, more like that second black line there. Now, so kind of an upside down laccolith, which tells us it was a diatreme. It was not a volcano. There was never a volcano there. What had happened is there was this magma chamber underground, and it needed to get to the surface, so it did. What happened is magma came up, stopped near the surface, and just kind of exploded. And I'm going to show you that model from the 2015 paper I mentioned before. Okay. So what you're seeing here is the paper published in 2015 in Geosphere, Devil's Tower, Wyoming, a lava coulee placed into a marred diatreme volcano. And this is one of the figures from that. And what you see here is they have A, B, C, and D. So they modeled a magma stock, a volcanic conduit or neck of a volcano, and a laccolith, and an inverted laccolith or diatreme. Well, the columnar jointing favors D by far. As you can see from A, the magma stock, you can see the columnar jointing kind of radiates volcanic conduit. It's pretty much, like I said, the flow would have been up, straight up, so your columnar jointing would have been perpendicular. We don't see that at all at Devil's Tower. When that hypothesis was first proposed, we knew very little about cooling of igneous rocks. And the laccolith, as you can see, it does kind of fit the laccolith a little, except the main trouble comes with the fact that you would have had columnar jointing kind of coming up like this, but on Devil's Tower it comes up like this. So D is what is favored. And they actually, here's another figure from it. I hope you can read that stuff on the right. If you don't want it, that's fine. I'll go through it. As you can see, 5A, you get the eruption. 5B, you get the magma. And it even shows you a little Devil's Tower, what will become Devil's Tower, the medium gray color in the middle. And it shows you the red, the magma as it's cooling, showing you how you did get some quartz in the surrounding stuff and then not quartz. So this eruption and this volume of pool of magma and in a depression which did not have a lake in it because we don't see that in tabular jointing, but this lava lake, not water lake, cooled to form this big huge inverted laccolith, and you can see the little Devil's Tower there, and the top of what is now Devil's Tower was close to, if not the original surface. So this fits very well with the observation. Well, just to be sure, they actually made a little diatreme model, and it was pretty cool. And here it is. You see A, B, C, and D. They made a laccolith, an inverted laccolith, and they cut it open to see what it looked like inside. And you actually get that the blue kind of into the gray kind of shows you the direction of columnar jointing would be. And it's not perfect, but you can see it kind of fits pretty well with Devil's Tower. Okay, there are transitions going on here. Lilith is going to move up into this room out from the basement. So there's not going to be very many more geophiles filmed in here. I'm going to have to move all this stuff out. But if you could, I'm going to link some of my book publications below if you would like to purchase them. At least you get something for your money. But anyway, I guess I'll just wrap it up here. I look forward to seeing you on the next Geophiles, which I think is going to be about igneous rock classification. But if you have any comments or questions, feel free to ask. That's it. I hope you learned something.